Another problem that I had meant to include in class 7 for statics review. It's from Beard Johnston, the 9th edition, and we want to determine the magnitude of the gripping forces that are taking place produced when you have 300 newtons forces applied as shown. And we have a whole bunch of dimensions, and we're assuming that we're taking our wrench similar to this right here, and we're putting forces right in there, and they're showing it like it's not in its toggled position. You can see when it's in its toggled position, these two things line up with each other, but now we're in a position where it's just cramping right there, right? And this toggle right here is a very powerful part of the thing. It really kind of, it actually kind of comes out, and then you see that we actually use this to break the toggle, right? So the toggle gets in. We know that these two things, when they're in line with each other, are very powerful. So just before it's doing onto the thing, right, we can see that we're putting a lot of mechanical advantage onto the thing. That's where a lot of the crushing will take place. So I'm hoping there's an interesting result when we do that homework problem that's similar here. But for this one right here, instead, we will use a little bit of geometry and trigonometry as we draw the thing out. So let's try this. I haven't solved this problem yet, so this I could fall on my face. Let me draw out this piece right there. Right, we're going to draw out this, and we have to be careful. We don't need to include all of the details here. All right, so right here, we're going to have a line, and right here, you're going to see, and they look like they're in line with each other, right? So let's make them in line with each other. And here's where these forces getting applied right here of 300 newtons right in there. And there's also a fighting force that's taking place. That's going to be right up here. Right there, right? So this is actually, and they're calling it the magnitude of the gripping forces, and I think it's just going to be upwards right here. So I'm going to call that G, right there. So we call that G for the gripping thing. So that's the thing pushing back onto the thing. So we're going to have forces coming up this way at B. That's going to be the FBY, and I'm going to have my FBX right here too, FBX. And I'm glancing at the solution manual, which isn't really going to do it the same way that I'm going to do it, so that's okay. And when we do the sum of the moments, we'll probably end up doing it about this point right here, this B, to be able to find this. And I'm going to say that this force, I'm going to take a wild guess that it's going to be upwards, right in there. And we want to try to figure out what this angle is going to be right here. So that I'll call that beta. So I'm pretty sure that we're going to have a force that's coming up this way right here. And that's going to be my FA right in there. So this is an FBD. And we might even want to draw out another FBD, this other part right here that goes between A and here. So we know that's going to be like a compression piece. So that's going to be our FA, and that's the two force member, which is sort of the key to this whole thing. All right. So let's take a look at what happens to this part of it right here. Okay. And we never actually take a look. I don't think we actually even need to ever take a look at this other part right here, because it's going to be, there's some symmetry taking place here. So I'm trying to think about how I want to arrange all of this. Okay, so I'm going to come down to this last one, say FBD. And let's kind of make sure that okay, these aren't on each other exactly. So I'm going to kind of draw them out. It's a little down like there. And then this one, we don't even say how far. I guess it doesn't matter how far much down this thing goes over here. But we have something that looks something like this right there. Right, so we're going to have this force right here that we're applying right here of 300 newtons, and here is going to be a force that's equal and opposite. It's going to be coming downwards right there, and we're going to figure out what that angle is right here in a second. And then we're going to have a pin force that's happening right here, right? So I don't know which direction that pin force is going to go exactly. I can kind of guess the x direction, right? Because I'm already guessing this direction right here. For this is my FC right there. It's onto C. I can guess that it's probably going to go this direction right here. So this is my FDX, and here's my FDY. And now I want to get, let me get that angle that I had meant to get. All right, so this is always like, got to be a little careful right here. Let's draw a triangle right in there to get our geometry. And so if that right there is going to be I decided to call it beta right there. I'm going to find that my beta is going to be, let's go rise over run, the inverse tangent of, it's going to be 36, right? It's going to be the rise. So this is 30 plus the 6, 36. And then the run is going to be, it's not 96, right? So that's 2 right there, right? That 96. It should be, it's going to be kind of confusing here. All right, so there's some geometry. There's some dimensions right here. All right, here's one that we know to be true right there. That this from here to there is going to be 156, right? 156 to get from here to there. To get from here to right here at C is going to be 72. So 156 minus 72 should be the distance between here and there. 156, 72 minus, we get 84. So that is what I am saying the angle is going to be. 36, and take the inverse tangent. We're going to see that's at 23.2 degrees. 23.2 degrees. And I'm just going to check what they're saying right here on theirs. They did a screwy thing where they took 1 over 8.84. What the hell are they doing with the 1.1? They're saying that this is a for that triangle. They're saying that this is a 2.5 to 1. Is that true? 2.5 to 1. They don't explain how they do it either. Is there an easier way to figure this thing out? I don't think so. Is 36 divided by 84, does that seem like it's 2.5 to 1? No. That's like 0.4. All right, so did I do something wrong? Let me double check my things here. 120 and 36 is 56. We agree with that. That's this distance right here. And so now I want to subtract out my 72. 156, 72 minus, that's 84. So I don't know if I'm going to agree with their values when they get it onto here. Yeah. Huh. Interesting. Anyway, okay, so I think I got the right angle right here. So when I come up for my distances to get to D from here, I take my this distance, because I'm going to take my sum of my moments about D. So the sum of the moments about D are going to be equal to 0, and that distance right here is going to be 96 plus 30. So is that 126? I think it's 126 millimeters in between here and there. So that's easy enough. But they say, yeah, they have 126. And now when we go, and then now they play around with the angles right here. I would prefer to, maybe I'll dash them in here, right? And I'm saying this is the beta angle right in there. This right here has a distance of 6 millimeters right here, right? There's the 6 millimeters right here. So here's 6 millimeters right in there. And then this distance right in here, that's a distance of 30. So when I go to write this thing out, I'm going to say that I have, going clockwise, 300 times my, and let me use millimeters just to make it a little easier here. Okay, so that's clockwise. Counterclockwise is going to be down right here in my vertical one. I take my FC, and that's going to be the cosine of my 23.20 degrees, right? Times an arm of 30. Now, if I take a look at my horizontal, wait a minute, I just messed up. My bad. Sine. I want the sine. I want the vertical one is going to be going times the 30. Okay, and now my the one is the cosine of this is actually going in the clockwise direction. So FC times my cosine of 23.2, and that's times my 6 millimeters. Okay, so let's see. Let's see how far off I get from theirs. They did something magical with their angles right in here. Okay, so that's going to come up the other side. I'm going to take my 30 times my 23.2 sine, boom, right there, and I'm going to take my 6 and my 23.2 cosine, multiply it, and I'm subtracting those, and now I'm going to divide that into there, and I'm going to say that I get for an FC is equal to 5,997. And they didn't bother with putting a number in theirs for some reason. They kept it as a number here, and they kept calling it FA. That's weird. I don't like when the way the solution manuals do stuff like that. I don't need to put that number in. I need to put their number 2863.6 and 8.84, and they send a square root and they multiply it. So they get 8,514. I don't like that. Let me pause. I don't want you wasting video while I get confused. Sorry. Okay, so here's something I found that I had messed up on. Makes it a little bit more clear. I misread their 2.5. They have a 2.8, and I think I took 36 here when that should have been only the 30. Remember that? I was going to C, not to D, so that should have been 30 here. So I got to fix my angle. And you say, well, you should just make a whole new video, but you have no idea how much time I'm taking up in this whole semester. It is crazy. So I want to try to make something that's helpful and useful, but I can't make them perfect. I don't think that's going to change my answer all that much. But we'll see here. They still did a crazy thing with their 2.8 over the square root of 8.84. Yeah, I'm still not liking that. I'm still not sure why they're doing that. So here's my 19.65. My 19. It's not going to change the answer all that much. See, I'll show you what they're doing right here. Okay, I have that answered, but they have this thing coming on right there, and I don't know why. Right? They're saying 2.8 divided by, and you can see here's the thing where I thought it was a 2.5. That actually says 2.8 to 1. But I don't know why they have the 8.84. It doesn't make any sense. Maybe that's the hypotenuse. Yeah, that's the hypotenuse. That's what it is. Let's just try that out right there. Is that 2.8 squared plus 1? Yes. And they're taking the square root. That's what they're doing right there. Okay. So let's make sure. Let's see. So my number, their number right here, should come out to, this is a 8.84 square root 2863.6. They're saying this should be 8,514 newtons. Whereas I was not getting that. So let me try to get their number. Let's see. We have 300 times 126, and I believe I have the right 19.65. Let me double check that this is supposed to be the sine. Okay, so for this one is going to be the counterclockwise coming down, and so I want to multiply it by the sine of that angle. Yep, and then times the 30 that's in there. Okay, I believe that. So I'm going to take the sine and multiply it by 30. Gotcha. Now I'm going to take 19.65. I'm going to take the cosine and multiply by 6. I'm going to subtract out those two, and I'm going to, now that's not going to work out. Divide through. No, I got it. Okay. 8,518. Right, so they're slightly off right there. Okay. I don't know what the math error was. You could probably find it in the video, what I had done when I was playing through there. So, okay, I've established what that force is, and I'm sorry it's taken so long. I wish I could edit these videos to get the shorter. Okay. So that's this line right here. Now I need to come up to this free body diagram, and using that I know this FC is equal to this FA is going to equal right here. I'm going to take the sum of the moments about B and place them on here, and hopefully I won't have the same amount of screw-ups that I had for this other one right here. So this distance to right here to B should be 156 plus 12, right? So 156 plus 12 should be 168, right? I hope so. 168 from here to there. And then these guys are in line with each other, so that's nice. This line right here is, so this should be 156 right here, right? I think so. So I'm going to take the sum of the moments, and also this distance right here between here and here is 36, because that's the thing we're trying to get. So we take our 300, and that's going counterclockwise, 168. This one's going clockwise right here, so let's put them in here as being negative 8518, but we're only going to take the sine of our 19.65 coming in there. And the moment arm was the 156, right? And then now the crushing thing is going to be counterclockwise as well. So that's going to be plus FG, and then that's times our 36 equals 0. Okay, so this one's going to actually, when we get to the mechanical advantage, it's going to have some serious problems, but we'll worry about that later. This is going to be 19.65 sine times, and our 156 times, right? Okay. And then but we're going to subtract out our 368. Hopefully that's the right one. We'll subtract that out. Now divide that by 36. And we get the wrong number. Son of a... What did you do? All right, so I have on here we only have 120. 120. Yes, you're right. There you go. There's where the mistake is. The mistake was waking up. No. 19.65 sine. Yes. Yeah, okay. And then take 300 and 168, which we probably screwed that up too. Yes, we did. We should do, that should just be, because we're doing it about B. That should be 132. We're going to subtract that out. Now we're going to divide by 36. Yay! We get what they got. Now that's going to be 8,448 newtons, right? So that's going to be the gripping thing, but we want to get the mechanical advantage, right? This is not a great one for mechanical advantage because I got to try to think what the torque in is going to be versus the torque out. It might be best to use a particular point as what you consider the torque in. And this is tough because this is what your homework is going to be like, right? And we're already at 23 minutes. Let's see. I'm going to say that this is the torque out to B, right? We're going to say this force times this 36. But here's the thing. Should we have just this load right here as a torque in? I think so. We should only use this piece in, right? So we're going to say, here's the torque in, and we're going to pretend like we're fixed in. Because if you're gripping something, are you putting 300 on both, or are you just doing 300 right here, and then this is the reaction? That's what that is. This is the reaction right here, this 300, and this is the 300 that you're actually putting in. You're not actually putting a total of 600 into the thing. You're only putting 300. That's what I think, into the thing, because it's equal and opposite, right? You're not Superman doing 600 right here. One of them has to be the reaction onto the other. So we put 300 in, and we might as well be having the same pivot point right here. So I'm going to say that and we could just even go for the mechanical advantage. We don't even need to put what the forces are. I guess we kind of do, right? Because it was not just a teeter-totter thing. There's also the linkages were involved. So I'm going to say that the torque in is going to be that 300 times that 12 and that right there was 132, and then the torque out is simply going to be the answer that we got, 8,448 times our 36. right? So 300 is going to be big numbers. Yeah, 132 times right there. So there you got 39,600. These are Newton millimeters. Should turn them into Newton meters, but anyway. And then we have the answer, but it's going to be times 36. Boom. And so we're going to have 304,100 Newton millimeters. So our mechanical advantage, according to me, right, is T out over T in. You can argue these. It's really supposed to be a measure of, just trying to see what the performance is, some performance parameter. So I get that it's a 7.68 mechanical advantage. But I thought it would be fair to do an example problem to help anyone that's trying to work through the homework problem. Sorry about all of the geometry snafus. I should have worked out this problem ahead of time, but time constraints, and it's a 26-minute video. So I hope somebody will benefit from this. It's not easy to do, creating this stuff, but